Any questions you have so that I can cater to your questions, or I start with shipbuilding material? Any questions you have? Any doubts you have? कोई डाउट नहीं है? फंडे क्लियर है मतलब? Okay, then we start back with our shipbuilding material. We do certain definitions because they come in your exams. So tensile strength, ये सब class 6th 7th वाला है. Tensile strength, malleability, ductility and all. So tensile strength is the amount of tensile or stretching stress a material can withstand prior to breaking or failing. So it is the force required to pull something like a rope or wire or a structural beam to a point where it breaks. Now your tensile strength will have three components. That is your yield strength, ultimate strength, and breaking strength. Now when you're pulling a material, the stress a material can withstand without permanent deformation, that is before the plastic. See, every material when it is pulled, it has got an elastic stage and a plastic stage. Elastic stage is when you pull it, remove the force, it comes back to original position. Plastic stage is when it doesn't come back to original position, so that is permanently deformed. So yield strength is a stress which the material can withstand without any permanent deformation. So it is not sharply defined point. So your stress will cause a permanent deformation of 0.2% and then will come back to its original position. So beyond your yield strength, the material will become a plastic. That means it will not become plastic. The ability of the material becomes plastic, that is, it will not come back to its original position. Ultimate strength is the maximum stress a material can withstand. After that, it will break. And breaking strength is the stress coordinates at the point of rupture, because after UTS, you don't have to pull it more, it will break. So the stress coordinates for breaking or at the point of rupture is breaking strength. So UTS, that point of UTS and breaking strength, and a ductile material is more and a brittle material will be less. Now I'll show you a full diagram here and then we'll do what is your stress strain graph. Then we'll come back here. So this is a typical stress strain graph curve which you have to draw when asked the question on stress and strain. And you have to explain each point on this. So from the initial page, this on the y-axis you have stress. Symbol is sigma, unit is Newton per meter square. Strain is epsilon, unit is meter. So basically, strain is it doesn't have any units. So how much it will be stretched, basically. So strain is normally how much it is stress, it will be centimeter or meter, whatever. So when you are pulling a material, it returns back to its original position as per Hooke's law. So your stress is directly proportional to strain, or sigma is directly proportional to epsilon. Limit of proportionality is a point till which the material follows Hooke's law. That means you remove the stress, it'll come back to original position. And the stress is directly proportional to strain till this point. In your yield point also, your the stress is removed, it'll come back to original position. Only that between limits of proportionality to yield point or elastic limit, the material will not follow Hooke's law. That means the strain is not directly proportional to stress. Beyond elastic limit or yield point, the material comes in plastic stage. UTS is the point where your maximum strain it can take, and break point is the point where it will break or fracture. So now we'll do the details. This was the basics which we have done in the stress strain curve. So the UTS is here, the fracture is point is here. This is the yield strength point where the distortion is 0.2%. Then it returns back to original shape. Now, what is ductility? Is when you are stretching a material to make it a wire. So the percentage elongation will be a metal's ductility, like a copper or aluminum. They are more ductile than iron. Gold and silver are also ductile, so you can make ornaments. So ductility is a measure of the degree at which your material can strain or elongate between the onset of yield and eventual fracture when you are under tensile loading. So the extent to which the bar stretches prior to your rupture is a measure of the metal's ductility. So ductility is a physical property of the material associated with the ability to be stretched into a wire without breaking. So ductile substance can be drawn into wire. Like your ductile materials are gold, silver, copper, erbium, terbium, and samarium. So this diagram shows how your copper metal can be pulled. So that is ductility, so you can stretch it. Now we come to malleability. So malleability is a property of the material so that it can be hammered into thin sheets like you have for aluminum, or you can have copper, or you can have for silver, which you have on your sweetmeats, or your sweets which have your coating of silver. So that is malleability. So the property of metal to deform under compression and take a new shape, or the substance ability to deform under pressure or a compressive stress, is malleability. So material may be flattened into thin sheets by hammering or rolling. So here you have the diagram of gold. It's the most malleable metal. That's the reason we can make a lot of ornaments. It is ductile and malleable, therefore it can be made into ornaments. Now, malleability is a property of the material being hammered into thin sheets without breaking. So you have aluminum foils, very malleable, and that's why you use to make wrap your food. Glass is not malleable. The moment you hit it, it'll break. Wood is not malleable. while copper is malleable. So these are copper sheets can be made because of copper is malleable. Now we'll come to hardness. Now why we have to understand the term hardness? Because we have a hardness test for steel, or shipbuilding steel will undergo hardness. So hardness is the resistance of a material to localized deformation. So you can deform a material by indentation. Indentation is you keep a heavy load there, it'll get bent, that area. Scratching or nail hardness is there. So will it have a scratch on the material? That is nail hardness, cutting or bending. So some materials are harder than others, like your plastics are and wood. And macroscopic hardness is characterized by your strong intermolecular bonds. But the behavior of solid materials are different under various forces. So you have various measures of hardness: scratch hardness, indentation hardness, rebound hardness. Rebound hardness is if you're sitting on that foam mattress, if it is too hard, it'll rebound, it will not compress. Because when you purchase mattress for your beds, you have to see which kind of mattress you're going to take. So you are taking natural rubber mattress, they are the costliest. When you got hard mattress, will rebound. So scratch hardness will be how much you can scratch on the material. Indentation is if you're pressing a hard material against it, will it get an dent there? And rebound is how much will rebound. So we'll study only indentation hardness. So hardness is dependent on ductility, elastic stiffness, plasticity, strain, strength, toughness, and viscosity. So if you see the hardness scale is the most hardness scale here. Diamond is the hardest here at scale number 10. At 9 you have corundum. That's also hard but little less than diamond. Then you got your drill bit, which is 8.5. Topaz is 8. Quartz, which you have in your watches, is 7. Steel nail is 6.5. Orthoclase is 6. The knife is 5.5. Apatite is 5. Fluorite is 4. Copper penny is 3.5. Calcite is 3. Fingernail is 2.5. Gypsum is soft at 2. And talc, which you have talcum powder, is 1. So toughness and hardness are two different things. Hardness is when you're pressing a hard object at constant force against that, you'll have an indentation. While toughness is measured by sudden impact. So you have an impact test, which we'll do later, for measuring your toughness. So suddenly, suppose your ship has a collision on the jetty. So the toughness is when your plate is not getting shattered or it's not breaking. That's the toughness because it can take the sudden impact. So toughness is the way a material reacts under sudden impact. Toughness is the resistance to fracture when the material is stressed suddenly. It is defined as the amount of energy the material can absorb prior to rupturing. And this can be measured in the stress strain curve by the area underneath it. So the entire area for a ductile material will be more tough than a brittle material because the area underneath the curve will be bigger for a ductile material than a brittle material. I'll explain with this diagram. Now, this is your ductile material. So the area under this curve will be much bigger as compared to the brittle material, which is just blue. So this is a tougher material as compared to the brittle material. So it is defined as the work required to deform 1 cubic inch of metal until it fractures. And it's the ability of the material to resist the start of permanent distortion, plus the ability to resist shock or absorb energy. So it is the toughness and ability or to absorb energy up to fracture or energy per unit volume of material. So this much is your toughness, high toughness for ductile rather than for brittle. So a tough material will have strength and ductility approximated by the area under the stress strain curve. So that will be A, B dash, C dash, C. That is the area under stress strain curve for ductile. For brittle, it will be ABC, much smaller as compared to ductile material. So that's the toughness. You're hitting this material, it bends, it is tough, but if it breaks, it is brittle. Now, fractures are two kinds. One is a brittle fracture and another is ductile fracture. Brittle fracture is very sudden. Ductile fracture is slow. So brittle fracture is caused because of lack of ductility. Suddenly your ship is going to very low temperature and they don't have any heat treated steel there. Then the steel plating might crack due to brittle fracture. That is the reason the ship's hull plating should be heat treated for cryogenic areas if you're going to those areas. You can't just enter that area if you have a normal shell plating. So it is a sudden, very rapid cracking of equipment under stress, where your material exhibited little or no evidence of ductility, or you have plastic degradation prior to your fracture. Both the conditions you'll have brittle fracture. So in brittle fracture, you don't have any plastic deformation prior to fracture. So you don't have an evidence of ductility or plastic degradation prior to fracture. So this happens very suddenly and the process is very fast. So it is involving little energy absorption. It occurs at very high speed. So brittle fracture will have quite less energy absorption. The speed of this fracture is very fast, 2133.6 meter per second. So it can crack the entire ship and it can sink within minutes. So in most cases, the brittle fracture will continue even when your loading has been discontinued. So means of avoiding becomes very difficult in brittle fracture once the onset starts. So the brittle fracture occurs in normal ductile steel when you have very low temperatures, primarily in large continuous box-like structure like box beam, pressure vessel, tanks, pipes, ships, bridges, and other restrained structures. So the brittle fracture that occurs in service are invariably initiated by defects, which are patent defects. Right from the very beginning, these defects were there, or not patent defects, inherent defects. Inherent defects are the defects which happened during manufacturing. So inherent defects से ये होता है because it was present during manufacturing, or it can be when the defects developed during the ship service. तो या तो वो inherent defects है right from the point of manufacturing, or it developed during your ship service period or ship's life. Now, brittle fracture is two types. One is transgranular and one is intergranular. So, transgranular is this one. It will go through and through the grains of the steel. So it is not going at the boundaries of the steel, but through and through the grains of the steel. The second kind is intergranular, which will happen at the boundaries of these grains. So here at the boundaries here, the crack will occur like this, not through and through. Through and through is transgranular. So transgranular fracture is a fracture that follows a crack through the lattice of the granular material, ignoring the edges of the grain in the individual lattice. And this results in fairly smooth looking fracture with fewer sharp edges than that follows a changing grain. So transgranular is much smoother as compared to intergranular. So the cleavage or the split in most brittle crystalline material, the crack propagation that results from repeated breaking of atomic bonds along specific planes leads to crack splits or cleaves through the grains. So this occurs through and through the lattice. It will not go to the edge, but through and through the lattice. The intergranular fracture occurs when the crack propagates along the grain boundaries of the material, usually when the grain boundaries have become weakened. So this is the lattices of the material. The crack develops here at the grain boundaries and follows here. It will not go through and through. If the crack is here, it follows like this. It will not go through and through. Now, brittle fracture takes place without apparent deformation or by rapid crack propagation, almost 3,133 meters per second. The direction of crack motion is nearly perpendicular to the direction of applied tensile stress and yields a relatively flat surface like this. So when a gradual tensile load is applied to the material in a tensile test, you're pulling the material apart in the tensile test. We'll be doing all the destructive tests later. So at the end of the elastic limit, without prior indication, the material will break. So that is known as brittle fracture. It will not give you advance warning. So this is the shape in a brittle fracture, and this is the ductile fracture. So this is much smoother as compared to cup and cone of ductile fracture. So your necking is formed and then this cuts off, and there's a cup and cone. So the cup is here, the material of this section is coming here, and because of the pulling is going to break here. So this is your ductile fracture, this is your brittle fracture. Now we come to ductile fracture. Now this type of fracture is characterized by extensive deformation of plastic or necking. You're going to pull the material. So yesterday you have seen the movie that the material being pulled and then it breaks at that point. That is necking. So necking is this section. show you that what is necking. So your necking is taking place here. This is necking. When you're pulling the material, the small strip, it becomes a big strip. So this is necking. So this is a necking formation formed and then the fracture effect. So the term ductile rupture is actually failure of highly ductile material because too much of tensile load is being put. So the materials pull apart instead of cracking. So in a ductile fracture, extensive plastic deformation or necking takes place before the fracture. So the terms rupture or ductile rupture describes ultimate failure of ductile material loaded in tension. The extensively plasticity caused the crack to propagate slowly. So instead of moving very fast in your brittle fracture, this is slow propagation. In brittle fracture, the absorption of energy was very less, but in ductile fracture, the absorption of energy is quite large. So the basic steps in a ductile fracture, you will have a void formation. Here you have a void formation, then void coalescence, crack propagation, and separation of the parts. So you have a void formation, void coalescence, crack formation, crack propagation, failure, resulting in cup and cone shaped failure surface. So voids typically coalesce around precipitates, secondary phases, inclusions, and at grain boundaries. Ductile fracture is typically transgranular, and deformation due to dislocation slip can cause shear lip structure of cup and cone fracture. So this is the diagram which you have to draw ductile fracture. So this is cup and cone fracture due to extensive necking. So another diagram of same. The necking is taking place, void nucleation, void growth, void coalescence, crack propagation, and fracture. Now, brittle versus ductile fracture, absorption energy is less, absorption energy is more. Energy here you can see is more. This will happen in cold temperatures, this will happen in high temperatures. So this is the difference between brittle and ductile. Now you have another definition which is fatigue. You might have heard that a ship 15-year-old or 20-year-old sank. So the fatigue occurs in most of the bulk carriers because of high stresses it incurs. That's the reason you have enhanced survey preparation programs for checking fatigues of strength of your various structures. In tankers, condition assessment program or CAP, you're checking the fatigue areas in the ship or tanker. So it is development and propagation of crack due to number of repeated alternative stresses like your hog and sag. So with the repeating stresses, you are creating a fatigue in the material which will crack. So here you have to apply a safety factor to create a fatigue limit so that you don't exceed it. So safety factor above the yield strength has to be applied since the steel regularly is pushed to yield strength will suffer from metal fatigue. So a steel will have a fatigue limit below which any quantity of stress load cycles will not cause metal fatigue or cracks and failures. So you should not cross your fatigue limit, otherwise you'll have cracks and failures. So ship's design criteria generally assume that all normal loads on ship times a moderate safety factor that should be below your fatigue limit. And it is wise to assume that the ship will be regularly operating fully loaded in heavy weather and strong waves, and it will encounter the maximum normal design operating conditions many times over its lifetime. But if your fatigue crack starts, then each loading cycle it is going to crack the same amount, small amount, then produce striations on some parts of the fatigue surface, and the crack will continue to grow until it reaches a critical size. So if you stop loading, those operations will stop. Brittle fracture, even if you stop it, continued, but this will stop. Fatigue crack will stop. So the crack will continue to grow until it reaches a critical size, which occurs when stress intensity factor of crack exceeds the fracture toughness of the material. When that exceeds, then that produces a rapid propagation and typically complete fracture of the structure. So to aid in protecting your fatigue life of the component, you have to undergo fatigue test using coupons to measure the rate of crack growth. So you're applying constant amplitude cyclic loadings and averaging the measured growth of a crack over thousands of cycles. So this is the fatigue. You have alternative stresses repeatedly. And in the fatigue test, you measure how many cycles of the stress you're going to have a crack. So how many number of cycles you will have to complete to create that kind of crack. So any questions of April batch and March batch? Any questions up to now? Any questions? March and April batch?
No, sir.
Okay, so we'll continue. So now we come to the points which we have to mention in your stress strain curve. The first point is your limit of proportionality. So the limit of proportionality here is the point, the stress strain curve, till it follows the Hooke's law. So that is a limit for following Hooke's law, where stress is directly proportional to strain, or strain is directly proportional to stress. Beyond limit of proportionality, it is not following Hooke's law. So it is the highest stress prior to which it will get deformed, and that increases proportionality applied. It is a point beyond which the Hooke's law is no longer true. When stretched steel. So beyond limits of proportionality, you're still in an elastic stage, but beyond yield point, you will not go, you will go to plastic stage. So limits of proportionality is not followed by a non-Hookean material like rubber, because that doesn't follow the Hooke's law. It will not follow limits of proportionality. But most other metals will follow it. Rubber doesn't follow Hooke's law. So your limits of proportionality can also be defined as the greatest stress which can be applied to elastic body without causing permanent deformation. Because in case your limits of proportionality and elastic limit are same, then it will be the greatest stress applied to elastic body without causing permanent deformation. But if your limits of proportionality and elastic limits are different, then up to limits of proportionality, the strain is directly proportional to stress. After it, till yield point, it will not be proportional. That means your strain will not be proportional to stress. So the proportionality limit is proportional to the area of cross section. So the material type and loading type will have no influence on the proportionality limit. Now we come to yield point. So yield point is amount of stress in a solid at the onset of permanent deformation, because after this you will have permanent deformation. So it is also known as elastic limit, which marks the end of elastic behavior and beginning of plastic behavior. So when your stresses which are less than yield point are removed, the material returns to original shape. Now this is another stress strain graph. So here you have elastic region, D is your elastic limit, C is your yield point, D is your UTS or ultimate tensile strength, and E is the breaking point. Now what is UTS or ultimate tensile stress? So it is the maximum stress a material can withstand while being stretched or pulled before failing or breaking. So it is a material's maximum resistance to fracture and it is equivalent to maximum load that can be carried by 1 square inch of cross section or cross sectional area when the load is applied as a simple tension. So it is the maximum engineering stress on uniaxial stress strain test. Now this area is strain hardening. This is wrongly mentioned strain hardening here. This area is strain hardening. This area is necking. So this is correct. Your stress is being applied. This is the limits of proportionality. There's a yield strength or yield point. UTS is here. Fracture point is here. Breaking point is here. So the point between your yield strength and UTS or ultimate tensile strength is strain hardening. The necking will start after this point. So after UTS, your necking will start and it will end with your fracture point where it breaks here. Now we come to the next term, which is modulus of elasticity. That is for measuring your stress to strain. So it is defined as a stiffness of elastic material. So it is also Young's modulus, and the ratio of stress to strain, that is denoted by letter E. So Young's modulus is stiffness of the elastic material, which is equal to stress by strain. So elastic modulus is a quantity that measures an object or substance resistant to being deformed elastically when the stress is applied to it. And the elastic modulus of an object is defined as the slope of the stress strain curve in an elastic deformation region. So a stiffer material will have higher elastic modulus, while a soft material will have low elastic modulus. Now coming to this diagram, you have this original length LO. You're putting a tensile stress. So your new length is ln minus LO, or new length is ln, and the increase in length is ln minus LO. So your strain is the change in length divided by original length, and Young's modulus is stress by strain. So your stress is force per unit area. The delta L, the change in length due to the stress applied. So Young's modulus states that stress by strain. So this is F by A divided by delta L by L. So eventually you will have F into L divided by delta L into A. That is your Young's modulus for your elongation of the material. So when you're applying a stress, E becomes that constant there because stress is directly proportional to strain. E is a constant there. That is F into A, F divided by A divided by delta L by L. So you will have F into L divided by delta L into A. Now stress, on ships you have almost 10 types of stress, but we'll do the stress on steel now. The stress is the force applied per unit area. So sigma is F by A. So you'll have tensile stress, compressive stress, and shearing stress. So your tensile stress is tending to stress the material because you're pulling it apart. You have compressive stress when you're tending to squeeze in. And shear stress is when your adjacent portion of material tend to slide against each other. That is shear stress. Shear stress I'll explain with a few more diagrams. Now suppose there's a nail on the wall and hitting from a hammer below. This section tries to move up and this section is here. So this is your negative shear. You're hitting the same nail from top. The right hand goes down. Left hand is still at the wall. So this is positive shear. So if you load your vessel partly here, full here, part here, full here, part here. So your buoyancy force will exceed your force of gravity here. Your force of gravity exceeding buoyancy, so you will have shear force or stress on this bulkhead. Similarly, you will have it here. Similarly, you will have it here and here. Similarly, I will explain here in this diagram how your negative shear is coming up, how the positive shear is coming up, how your shear is acting at the tank boundaries. So shear can occur axially or it can be athwartly or it can be on sideways, it can be top to bottom. So bending moments you'll be doing later in your stability. Now, suppose this is your shear forces. So, this is a vessel which is loaded with various loads in the tanks. So, your shear forces are 5 Newton, 5 Newton, 5 Newton, 5 Newton, 6 Newton. These are the negative forces, positive forces are down. So bending moments, you're multiplying the distance, perpendicular distance from your arc perpendicular. You can take it from forward perpendicular also. So you multiply the distance into the force, you get bending moment like 5nx. Here you have 3x into 5, 15nx. Here you'll have 36. We have minus 72nx. So here you have a sag because the positive is more than your negative algebraic sum. So you have a sag in your bending moment here. This you'll be studying in your stability, or you will have these questions coming up to make the graph of. So tensile stress is tending to stretch or lengthen the material. Compressive stress is tending to compress the material. And shearing stress is tending to shear the material across. Now we come to what is strain. So strain or epsilon is the change in dimension divided by original value. That is dl by L. So strain is dimensionless because when you divide meter by meter or inch by inch, you will have no dimension. It's a ratio. So dl is an elongation or compression of the object in meters or inches or centimeter, and L is the length or original length of the object in meters, inch or centimeter. So when you cut meter by meter or inch by inch or centimeter by centimeter, it will not have any dimension. So strain is a physical change in the dimensions of specimen that results from applying a load to the test specimen and is calculated by the ratio of change in length and the original length, which is deformation. So the change in length, original length is your orange, the change length is yellow plus orange. So epsilon is delta L divided by LO. So it is dimensionless. When the units are given, they are usually in inch per inch or mm per mm. So change in dimension divided by original length will have strain. And percentage elongation is strain into 100%. So that is percentage elongation. So stress is force per area. Strain is change in length by original length. So this we have done this graph. This point is limits of proportionality. This is yield point. This is the elastic phase. This is the plastic phase. So between this point to UTS, you have strain hardening, and between UTS to break point, you have necking. And the entire area under this curve will be for measure of toughness. So UTS is this point. This is the break point. Stress will be Newton per meter square. Strain will be dimensionless. So chalo, let's take a break for 15 minutes and we'll resume with your shipbuilding material after the break.
Okay, sir.
is proportional to stress. So when the body changes shape within your elastic limits, the ratio of stress to strain remains constant. That is equal to E. And the curve, if plotted, would be straight line. So E is stress by strain. So Hooke's law only holds for certain materials under certain loading conditions. So for steel, it will exhibit a linear elastic behavior, and that is valid for throughout its elastic stage. So that is whenever your stresses are below your yield strength. Now for aluminium, the Hooke's law is valid only for a portion of elastic range. And for these materials, a proportional limit stress is defined, below which the errors associated with linear approximation are negligible. Rubber is basically non-Hookean because it doesn't follow Hooke's law, because the elasticity is stress dependent and is sensitive to temperature and loading rate. So if your temperature rises, it will stretch. The loading rate increases, it will stretch. So there you have to be very careful of your hoses. So here you have stress strain curve for low carbon steel showing relationship between stress and strain. So the Hooke's law is valid only certain portion of curve between origin and yield point. So here you have yield point, and this is a rupture point, and this is a different kind of steel. We'll come to what kind of steel is this. So your necking range is 5, the strain hardening range is 4. Now the various materials stress strain curve. For a brittle material, it is going sharply up, the gradient is pretty high. For a plastic material, the gradient is very low. So the toughness is less because the area under this curve is very less. Ideal material is ductile. Area under the curve is pretty high, so it is tough. And this is a strong building material which is not ductile, so it is not that tough. Brittle material is also not tough. Now you have stress strain relationship of the various metals. This is aluminum, copper, mild steel, and nickel, chromium, molybdenum steel. And this is Hadfield steel, which is used for your helmets. So this steel, if you see, even if you put too much stress, the strain will not be much. So the fracture occurs only after too much of strain. So this one is ideally used for helmets. This is Hadfield steel. So we have done your stress strain relationship, and now we'll continue with your steel. So what are the properties of good steel, shipbuilding steel? One property is the carbon content should be below between 0.15 to 0.33%, and it should be suitable for flame cutting and easily welded. It should be ductile. It should be homogeneous composition to prevent weakness in the material. It should have a high yield point and higher ultimate breaking stress. It should be resistant to corrosion, and the cost should be reasonable. So the carbon content is very important in the various steels, because if it is too high, that means the material will be brittle. So the ideal content is 0.15 to 0.33. Now the types of iron, we have pig iron, we have wrought iron, We have high tensile steel, we have cast iron. So we'll be doing the various types of iron, and then we'll have a video on these kind of irons. So pig iron basically is a raw material for cast iron and wrought iron. So because you're doing smelting in the furnace, so after slag removal, the first iron which you get is pig iron. So it is formed by treating sponge iron or directly reduced iron so that it loses your affinity to water and becomes more stable. So pig iron is intermediate product of iron industry and known as crude iron because you can't produce anything out of it. You can't make any metal out of it. It has a raw material for cast and wrought iron. So it is obtained by smelting iron ore in blast furnace along with this bauxite. So that is used for, not bauxite, it is used with another material is used for melting it to produce slag, and the slag is removed, and then this pig iron is produced. I'll show you a movie on this. Pig iron has got very high carbon content, typically 3.8 to 4.7%, along with silica, and that makes it very brittle. So the use of this material is except for as a raw material of cast iron and wrought iron. The other use is not much. This is pig iron. Now we come to cast iron. So cast iron is produced by melting pig iron. So we come to cast iron. So cast iron basically is produced by melting your pig iron with layers of coke and limestone. So limestone is calcium carbonate. That is after melting, you're pouring into molds. That's why you cast iron, because you're putting in molds. Then you can make your shape as required. So the carbon content is high, but not as high as pig iron. So this is 2 to 4%. So now the strength is high, but your carbon content is more, so it becomes brittle. So cast iron is group of iron carbon alloys with carbon content greater than 2%. But the usefulness is that the melting temperature here is low. So with this relatively low melting point, good fluidity, castability, excellent machinability, resistance to deformation, and wear resistance, you can use in pipes, machines, automotive parts, cylinder heads, cylinder blocks, gear cases, and it is resistant to damage by oxidation. So here you can see the valves are prepared with cast iron. Your bits on your ship are made of cast iron. These cannons made of cast iron. Uh, the valve wheels are made of cast iron. Now we come to wrought iron. Wrought iron is basically melting of pig iron with silica in cold fired furnace, and after that it is drawn or beaten into shape when it is still hot. So the heat treatment is given and it's beaten into shape while being hot, and it's become wrought iron is made tough. So that heat treatment is given for making it tough. So the product is extremely ductile. You don't have any brittleness. So it is used for anchor and cables. So because your anchor are tough, so even after dropping so many times, it doesn't break. So your carbon content is quite low as compared to cast iron in wrought iron. It's because the carbon content is less than 0.08%. Now, because of this being very low, this is tough. So it is a semi-fused mass of iron with fibrous slag inclusions, and it gives you grain resembling wood-like structure. So if you see the cutting here, you can see a lot of grains in wrought iron. The properties of wrought iron are it's soft, ductile, magnetic, highly elastic, tensile, strength is there. It can be heated and reheated into various shapes, but you can't make it hard because the thing is carbon content is low, so you can't make it hard. So although wrought iron exhibits properties that are not found in other forms of ferrous metal, it lacks carbon content necessary for hardening through heat treatment. So the applications of wrought iron are pipe making due to superior corrosion and fatigue resistance, better welding, threading qualities. It is also used for making bars for stay bolts, engine bolts, rivets, because it is corrosion and fatigue resistance. It can be used for making plates, can be used for special chains and crane hooks because it's got high impact strength and good weldability. Then it is used for forging application, that is for nuts and bolts. So here you see Eiffel Tower is made of wrought iron. Iron pillar near Qutub Minar is made of wrought iron. So that's why you don't have any rust on it for thousands of years. These are your fencing made of wrought iron, your chain hooks are made of wrought iron, implements made of wrought iron. So that is your wrought iron application. So आज यहीं तक कराते हैं क्योंकि बहुत ज़्यादा हो जाएगा अदरवाइज तो वीडियो
ये झाड़ी
दिखाते
को
हैं
रोटी में करके बना देते हैं
सीमेंटाइट और टेक्टोइड टेम्परेचर ये सारा आपको वीडियो दिखाता हूँ इसमें
about blast furnace used for extraction of pig iron from the iron ores. Now we will discuss about the parts of the blast furnace. We have a shell with charging door. This is a charging door from which we will charge the furnace. The cell with refractory linings. These are the refractory linings for preventing from the heat loss. There are blowers left and right hand side to supply air to the furnace for the complete conversion of the charge. From height, this is the stack. From this height to the upper portion of the furnace, this is called stack or chimney. This is called hearth. The lower portion of the furnace is called hearth or also well. Tap hole for collecting the molten metal or collecting the pig iron from the furnace. Now we have a layer by layer ore, coke, limestone or coke. Limestone will act as a flux which will combine with the impurities of the ore and make a slag, and this slag will be extracted further. Now layer by layer ore, coke, limestone or coke will be thrown in the blast furnace. Now this charge door will be open and layer by layer ore, coke, limestone will be placed in the furnace. Then what will happen? Three layers will be made in the furnace: molten iron, molten slag with the combination of limestone with the impurities of ore, and conversion. There are three layers will be out, and molten iron layer will be lower layer of the three layers, and this molten iron will be from this hole. This blower will supply the air in the conversion region. This blower will rotate and supply the fresh air to the furnace. This will be extracted from the hole in the outside. So this is the working of blast furnace for extracting pig iron from the iron ores. Thank you.
Blessed admin suit class.
कि सर ने बोला था कि 3
Where I feel like is a very tactile, intimate product. I mean, it's something that someone who has it at home is using every day. Their food is touching it every day. And so we're very specific about how we treat that surface. We're only trying to make products that will last forever, that are useful. The process informs its value.
We start everything off with a digital file and we machine all of our own patterns, so that helps us with the design process because we get to live with things for a while. This side would make the mold for the interior of the Dutch oven, and that's the outside.
Among like cast iron devotees, there are two camps, like people who really prefer vintage cast iron from the 30s and 40s, which has very thin walls and is polished super smooth. And then modern cast iron is generally very thick and heavy. So our skillet is sort of a combination of the two camps. It is on the heavier side because that is what cast iron is good at, but then we spend a lot of time smoothing it down.
With the mold making, it's kind of just an attention to detail and a level of practice. So we use a new sand for the very face of the mold, just a mixture of sand with a little bit of resin binder in it to hold it together. New sand is really angular. All those angles kind of mesh with each other and form a really smooth surface. But then the bulk of what we're putting in the mold is reclaimed sand. It basically takes practice how quickly to pack the sand together so that when you pull it off of the mold, it doesn't leave all the letters and the logo behind and things like that. There are a lot of details to the pieces that need hand finishing and need the types of molds that we make. We add a ceramic filter to the gate. It's a little piece of foam, so it filters any impurities that are left over the iron oxide film that forms on the surface of the metal. Being in control of the whole process and doing it at a really small scale, we don't have to compromise on those things. We can make exactly the piece that we want to make. It adds labor and it adds time, but I think that we get the result that we want in the end. We've got a small induction furnace which melts about 200 pounds at a time. The way it works, kind of like an induction stove, this uses the magnetic field to melt the metal down. Cast iron is always an alloy of iron, carbon, and silicon. You can play with those to give it different properties. I think of our raw material as being these post-consumer things. You know, our raw material is a scrapyard full of brake rotors because there's just so much of it around. The temperature is tricky because there aren't very many good ways to measure it because as you stick something in it, it melts. The way that we do it as we're pouring is to just look at the color of the metal and kind of get a feel for what it looks like when it's ready. And it has to be just right so that it doesn't freeze before it fills the mold up, so that it isn't so hot that it burns into the sand and makes a really rough surface. We add carbon and silicon to it to make it less brittle and less hard, because otherwise we wouldn't be able to sand it down. We've kind of tweaked it over time through trial and error to make the material what we want. Part of the pouring process is learning to pour at the right speed, filling the mold up just fast enough that it doesn't freeze before it fills the mold. Then it solidifies in a matter of seconds because it's coming from 2500 down to room temperature. And not so fast that it's creating turbulence and affecting the surface finish. So that's been something that I've kind of acquired over years of doing it, is the temperature and the pouring speed and the angle and everything just right. So after it's cast and cooled down, we drop the mold onto the shakeout, which is a machine that vibrates.
स्टार्टअप करने की सबसे मुश्किल चीज पता क्या है? It's not selecting the idea, it's not selecting the team.
Let it kind of disintegrate, and it has a series of screens inside to screen the sand into smaller and smaller pieces until it is back into sand grain form and we can reuse it.
After the skillets are cast, we take the surface of the metal down from its rough finish to like a really nice smooth surface. You use different variations of sandpaper until it gets to the fine surface that you want. John and I both come from art backgrounds. It's our predilection. I think by making these things by hand informs so much of what it is. The idea that like you're getting this tool that was made for you, and just that it took a lot of care to do it.
You know, one of the things about a cast iron skillet is that the handle's always too hot to pick up. That was one of the starting points, was to figure out how we could make one that you could pick up.
The heat dissipates through the fork connection, and then there's less mass in the handle also to hold the heat, so it's cool to the touch when you're cooking with it. Has a pretty thick base, so again, it's good at what cast iron is good at. It has this big helper handle to make it easy to maneuver.
We've got the Dutch oven, so our casting is a little bit thicker than a typical Dutch oven. And then on the lid, it has these little pips on the lid, kind of recirculate the moisture inside.
It sort of contains a little climate inside the Dutch oven, and the weight of the lid helps not let that steam escape too.
The other thing we wanted to do with this is cast the handle into the lid. You can't melt it off. It's not going to come unscrewed over time. We worked on a lot of the details of the Dutch oven with longevity in mind. We have kind of two directions that it can go in after finishing. So we can season it or we can enamel it. Both of those things need
Wrought iron. What even is this stuff? Wrought iron is the material that has been used for centuries before us by smiths. And it's disappeared for good reasons, and I'll cover that a bit later in this video. But first, what is this material and what does it even look like? When this material, that is wrought iron, is newly produced, which it isn't anymore sadly, but when it's newly produced you cannot really tell the difference between this and mild steel. It will be difficult to tell the difference just from the eye. You're going to have to look a bit deeper and look for other key details that will tell you whether this stuff is wrought iron or not. The first thing you'll really notice with wrought iron, especially if it's used in old buildings or anywhere else, is that it has a particular rust pattern when you look at it. Usually you can see it in old anchors and chain. When it rusts, it actually exposes the layers that are on top of it, which you can see here. Hopefully you focused. There we go. You can see that it's got layers, sort of like Damascus or pattern welded steel, if you will, but this is practically the same material throughout. So it has that particular rust pattern. Another way you can sort of conclude that it has to be wrought iron is if the building is very old and the iron parts that are in the building have been there for a long time. Say the building is from the 1600s. Likely it's going to be wrought iron. It has to be wrought iron because they didn't have mild steel at the time. Mild steel is very modern. Unless there has been, I wouldn't call it a restoration, because a restoration means that you bring it back to its original state. If you then use mild steel, that is not original, so technically you don't really have a restoration, but you have a repair job. But if it's still there after 300 years or more ago, it's going to be wrought iron because we didn't have anything else. Of course, we didn't have steel, but it's not the same steel that we have today. It's totally different. Apart from rusting, you can also have a closer look at what the material does when you break it, because that is very different from mild steel. I got a bit of mild steel bar here, and I've done a nick and break test right at the end here, so you can look on the inside what that structure looks like, and it's very different than what wrought iron is. If I bring that close, you can see it's sort of a bit like taffy, very consistent and not very particular. It's quite consistent. This is just mild steel bar.
If you can't find a way to make money while you sleep, you will have to work till you die.
Now this is a wrought iron bar from an old windmill, an old Dutch windmill. And we take a look on the inside. You can see that of course it's got some rust from time, but I've left it open like that. You can see that the break on the inside is very fibrous. It's almost like there are threads in there. Now, why doesn't it even have this? Because why would this material break like that? Well, it's because it's actually, like I said before, it's built up out of different bits of iron, different bits and layers like that. It's not like they put one layer on top of each other and then welded that, you know, like this very thin layer and then another one and then another one and then another one until they got that bar. No, that's not, well, technically you're right, and you can actually do it that way, but it's not a very efficient way of working. It's much more efficient to, if that would focus please, it's much more efficient to take a larger bars and join them together and then draw that out. It is actually very similar what I've done with forge welding these nails together. In a similar way, of course they don't start with nails, that doesn't make any sense, but they'll start with a sponge-like material, whether that is charcoal iron or puddle iron, which I'll cover later, but it's either charcoal iron or puddle iron essentially, and you join the blooms or the sponge-like material into a bigger cluster, and then you draw that out into a new bar. That will result in these lines. So they're similar like what has happened when I joined and forge welded these nails, which I of course turned into these mini tongs. The alloy is also very different, whereas mild steel is quite clean. Mild steel is quite a clean material relatively. It doesn't contain the slag that this material contains. You know, the sort of glass-like silica threads that are in there. That naturally comes with refining this material, but it's got different properties. Essentially, there are two types of wrought iron. The first one is charcoal iron, and the second one is the more modern variant, that is puddle iron. Charcoal iron is what they've used in the Middle Ages and before us, and they produced that by smelting. That's not the same as melting, but by smelting iron ore in a charcoal-fired furnace and then getting rid of the oxygen and any other types of impurities and turn it into a bloom. Now, you shouldn't mistake this with cast iron, because cast iron is totally different. Cast iron means that the iron has actually been liquefied. In a bloomery furnace, this doesn't happen. It stays a solid and it sort of clumps together. Heat it up and you forge weld it back together in order to drive off whatever impurities are in there, in order to close those gaps that are in there that naturally form. This material, when it's produced, generally doesn't take up a lot of carbon, so it stays mostly iron and, you know, the glass, silica type of stuff that stays in there and sort of lives alongside with the iron is what you're left with. It's rather soft. It's not that great for swords. It's not great for knives. Of course, a butter knife you can make out of it, just a general purpose knife, but nothing that can actually hold an edge very well over long periods of time. The more modern variant of that is puddling iron. And what they do with puddling iron is actually taking cast iron, which they could make with a coke fire, which they melt it down. But the thing with cast iron, even though we say it's cast iron, it's actually steel with too much carbon. It's too much. You cannot forge cast iron. In one forge, it's very brittle, so you don't forge that. What they then do is, just you imagine you got these, you know, these bars of pig iron, and they got to be turned into something useful. And they want to get rid of the carbon that's in there, so they burn it out. They use a puddling furnace for that, and it's either I believe they can even use charcoal, but they use coal. I know they use coal for that, and you can use coal to heat up the cast iron. You know, draw the gases over it in order to get it to a molten state, and then you stir it, and then you try to stir it up as much as you can in order to get the carbon to burn out. And then at a certain stage, as the carbon goes out of the cast iron, the more carbon is released, the higher the melting point will be. And at a certain stage, it will also turn into a sort of like sponge-like material like this, and then it can take that out of the puddling furnace and turn that into new bars. And that is what this stuff is. This is not charcoal iron. This is charcoal iron. But all this stuff, what I got here, is very likely, and I'm quite sure, is all puddle iron. And all these methods, you know, to produce this iron are very expensive. And the thing with this material is, it is quite nice to forge with. It's got quite good forging characteristics because it's soft, so it doesn't require as much effort from the smith. It also has some corrosion resistance because of the inclusions that are in the iron by itself. That is from the refining process, whether it's charcoal iron or puddled iron. Puddled iron can differ a tiny bit in its quality depending on what type of fuel they use, whether it's good quality coal or coke or whatever they use to heat it up. If you got some dirty coal with sulfur and
This was very deep and very excellent. And the teacher is too good.
Alright, in this video, I'm going to show you the difference between high carbon steel and mild steel. So I got high carbon steel on the left, mild steel on the right. They are of the same thickness. They're roughly, I believe, around 14 gauge. Now, I've been getting a bunch of comments on my ring videos that I have on my channel that when I quench the either steel nut, that I'm indeed hardening it. And I'm also getting some comments on coin videos where if I quench the coin in water, I am hardening it, which typically, if it's an American quarter, it is actually made out of a non-ferrous material, which you cannot harden by quenching. So I'm going to show you the difference right here and put that to bed. I'm going to heat these both up with a torch, quench them in water, then I'm going to try bending them, and then I'm going to try cutting them or running a file on them, and you'll be able to see the difference, the stark difference between the two. It would be awesome if you could harden mild steel, because then I wouldn't have to search for high carbon steel for making springs or making knives, something that needs to be hardened so it can hold an edge, or so it can actually be springy when you heat treat it properly, depending on your application. So let's try this. First up, mild steel. Okay, that's mild steel. I'm going to put that aside. Now I'm going to do high carbon steel. So here are the two pieces of steel. I'm going to clamp in the vise the mild steel first. Okay, first thing I'm going to do is I'm going to take my file. I got a file right here with a sharp tip on it. I'm going to scratch it. And see how it digs in? Digs right in with ease. See, it's even peeling up some of the steel. No problem at all. This is the high carbon steel. Skates over the metal. If I work at it long enough, it'll just ruin my file probably. But see, skates over it. Let's go back to the mild steel now. Bend test. I've heated this part of it right here. If I bend this, if I pull on this, or I should say apply a force on this, this should bend. And look, it bends, no problem, super malleable. I'm bending this with my hand, not an issue. Okay, mild steel. Come back to the high carbon steel. I'm hitting it. Doesn't bend. Snaps. That is because it was hardened. So this was the high carbon steel that snapped. I'm going to take the other piece. I'm just going to heat it, let it cool on its own, and show you that this wasn't some magical steel that was different, that it indeed will bend. Alright, so it's cooled. I'm going to take my pliers, and then as you can see, instead of snapping this time, it bends. All day. And then this piece up here, where it actually kind of got tempered, is actually kind of become springy now, depending on how you temper the steel after heat treating, because this part up here originally I had heated and then snapped off. But because I had heated up to about here, this here didn't get up to the point where I forget the terminology of the crystallization of the steel, but it hasn't fully converted to the material that is to the, I guess, the substance. Is it marsenite? I forget exactly. Anyways, if you Wikipedia, it's in there. So it's remained springy here. So I can't really bend it, but it's not snapping. So you consider that spring steel or tempered. But this part here is fully malleable. So I hope this video has helped clear up the differences between mild steel and high carbon steel. Typically nuts that I'm using to make rings out of are made out of mild steel. So if I heat it and then quench it, all I'm doing is speeding up the process of cooling it down. I am not hardening it whatsoever. So this can be applied to any type of steel, particularly steel has iron in it, meaning it's ferrous, as opposed to non-ferrous metals that also you cannot harden by quenching. You can work harden some of them, but you can't heat them up and then quench them and expect them to harden.
अच्छा लगता है यहाँ आना. पहले तो कभी आए, कभी नहीं.
हेलो दोस्तों, मेरा नाम है नीतीश और आप देख रहे हैं फोर्स यानी कि एजुकेशन फॉर सिविल। चलिए शुरू करते हैं आज की इस वीडियो।
Hi, and welcome to Metal Supermarkets, the convenience stores for metal. I'm Jason Jackson, Operations and Development Manager. In our last video blog, we reviewed the various categories and classifications of steel, along with the AISI and SAE numbering systems used to identify the different grades. Remember, a helpful way to remember the 4 types of steel is to use the acronym CAST, which stands for carbon steel, alloy steel, stainless steel, and tool steel. In this video, we will take a closer look at C, carbon steel. Carbon steel can be segmented into 3 main categories based on the carbon content: low carbon steel, sometimes known as mild steel, medium carbon steel, and high carbon steel. Low carbon steel is one of the largest groups of carbon steel with shapes including bars, tubes, sheets, and structural beams. Carbon steel typically contains 0.04% to 0.3% carbon content. Depending on the desired properties, other elements can be added or increased. For example, with drawing quality steel, the carbon level is kept low and aluminum is added. For structural steel, the carbon level is higher and the manganese content is increased. Medium carbon steel typically has a carbon range of 0.31% to 0.6% and a manganese content ranging from 0.06% to 1.65%. This makes the steel stronger than low carbon steel, but it is more difficult to form, weld, and cut. Medium carbon steels are often hardened and tempered. High carbon steel, commonly known as carbon tool steel, typically has a carbon range from 0.61% to 1.5%. High carbon steel is very difficult to cut, bend, and weld. Once heat treated, it becomes extremely hard and brittle. Hopefully this has given you a better idea of the types of carbon steel. In the next part of this video blog series, we will look closer at the A in CAST, alloy steel. If you need steel for your next project, Metal Supermarkets is the world's largest supplier of small quantity metals, carrying over 8,000.
Okay, we'll have a lunch break now.